Today, we're going to talk about batteries. There's a little problem with batteries. And the problem with batteries is going to be even a bigger problem after we name it, because the name that we gave the problem is worse than the problem itself, because it's a stupid name. The EMF, the electromotive force, which is not a force, but a voltage, was named before we knew what voltage was. But EMF just means the thing pushing the electrons, which is really a voltage, right, and not like a force so much, although there are forces involved. The EMF is the voltage of the battery, which sounds like a dumb thing to say. Why don't we just call it voltage if we're going to call it EMF? And we use this little script 3. It's not a 3, it's an E. I was thinking in my mind backwards 3, which is what it looks like. And I said 3. This is a good recording. I'm glad you're listening. All right. So a little script E is the V of the battery. But the reason that we're going to use EMF or electromotive force or script E is that the voltage of the battery is not the voltage of the battery. Because the battery is a big bag of chemicals that can produce a certain amount of voltage. But producing that voltage takes energy. And the electrons, as they go through the battery gaining energy, actually use energy in the battery as they gain it, which is called internal resistance. So the internal resistance of the battery assumes that the battery itself is a resistor in series with the rest of the circuit. And so the voltage supplied by the battery, you have to subtract out the voltage dropped by the battery itself. So if it's a 1.5 volt battery, but it's got some internal resistance that drops 1/10 of a volt, effectively it's only a 1.4 volt battery. And that's the little complication. So the equation that we'll get, or the assumption we're making, is that between the terminals of the battery is both a voltage source and a small resistor. We're just going to make that assumption that it's in there. And notice my little asterisk here. We're going to assume that internal resistance is 0 unless otherwise stated. Like the problem that you get on a test, for example, will state it has internal resistance, and then you have to find it. If it doesn't say that, you can assume it's an ideal battery. But the EMF is the source voltage, the nominal voltage of the battery, without taking into account its internal resistance, which means that the terminal voltage of the battery can be calculated like this. V, the terminal voltage of the battery, is the EMF, that is to say, like the nominal produced voltage by the battery, minus the internal resistance. Internal resistance is not IR, it's current times the internal resistance, right? But it's IR, so it sounds like that's an abbreviation, but it's like not, it's a fake abbreviation. So you take the full EMF of the battery, subtract out the voltage dropped by the internal resistance of the battery, and that's going to give you what we call the terminal voltage. Okay, and that is the voltage from terminal to terminal of the battery, what it can actually do. This equation, V equals script E minus IR internal, is a good equation to add to your equation sheet. Or, for the 8th time this year, you can reprint the new updated version, if you'd like, because it's now correct, because it's another one that I forgot. Next year, man, those guys are going to have it easy. All right. So, again, what we care about is this idea of a terminal voltage, the voltage from terminal to terminal, A to B, including the internal resistance of the battery. That is actually going to change. Right, if you have a 10-volt battery with 1 ohm of internal resistance and you connect it to a 1 ohm resistor, how much voltage does your battery drop? You have a 10-volt battery, you got an ohm of internal resistance and an ohm of external resistance. That internal resistance drops half your voltage. Right? 1 ohm, 1 ohm. It's going to share between the two 1 ohm resistors. It's going to share evenly. 5 volts gets dropped here, 5 volts gets dropped there. If you have a 100 ohm external resistor with a 1 ohm internal resistor, then the voltage outside is 100 times bigger than the voltage inside. So the size of the external resistor actually changes how much your terminal voltage is, because the internal resistance of the battery will drop voltage proportional to the rest of the resistance in the system. So the battery's size and strength depends upon what it's connected to because of its own internal resistance. All right. So let's see if we can figure some stuff out. I'm going to take a battery, which is everything between points A and B down here, which is including a 12-volt voltage source and a half-ohm internal resistor. We're just going to pretend like it's a resistor. It's not, but we're going to pretend like there's just one in series there. And I want you to tell me a couple of things. Tell me the total current pushed in the circuit. Tell me the terminal voltage of the battery. That is to say, it's not 12 volts. It's less than that. Tell me what the voltage is of the battery after the battery. And then give me the power dissipated by both the resistor R and the internal resistance of the battery. Tell me how much voltage, how much power is dissipated by each. Okay. Ready, go. To find the total current in the system, we need to remember that we do not have just one resistor, but two. So we're going to say that the voltage dropped across the circuit is 12 volts, but we're dropping it over 65.5 ohms because we're putting that in series with the half-ohm resistor in the battery, which it's not like a little resistor in the battery. It's the equivalent of a perfect battery with a little half-ohm resistor. And we're just going to say whatever's going on in there, it's like it's a half-ohm resistor. So it's 0.183 amps, not 12 over 65, because that would assume that there was no internal resistance, but there is. So we're going to get a little slower current. It's 0.183 amps. And then if I want to find the terminal voltage of the battery, I use that equation that we just talked about. I say, hey, 12 is my EMF, and I'm going to subtract out of that the internal resistance of the battery, which is the current through the battery, 0.183, times the resistance of the battery. All of this ends up being about 0.1. It's a tenth of a volt dropped by the battery itself, which means the terminal voltage is 11.9. Now, if we have a smaller resistor, if the two resistors get closer in size, if either internal resistance gets bigger or the external resistance gets smaller so that proportionally they're closer together, then the terminal voltage changes, even though the EMF stays the same, because that's just how much it's pushing, regardless of the internal resistance. You with me here? Everybody good? Questions? Cool. Power is V times I, 11.9 volts dropped across the 65 ohm resistor times the current going through that resistor gives me volt amps or watts of 2.18, 2.2 watts. That's a light bulb just giving off 2.2 watts. A watt is a joule per second as much as it's a volt amp. In fact, a volt amp makes a lot of sense that way. It's the question that I took off of the last test because it should have been on the next test and we missed it. But a volt is a joule per coulomb, right? And an amp is a coulomb per second. So what's a volt amp? Joule per second. Hey, it's a joule per second, which we call a watt. Volts times amps is watts. So a joule per coulomb and a coulomb per second gives me a joule per second, which means I get watts of power. So if I'm pushing so many watts, that means that that's how much energy I'm releasing. So if we go back to this problem, 2.2 watts means 2.2 joules released per second. 2.2 joules of energy, of light energy or of heat energy or whatever, per second of time that goes by. That's how much energy I'm releasing into the system. That's how we're going. All right, the battery drops a tenth of a volt at 0.183 amps, which is 0.018 watts, 2/100ths of a joule per second. And that's our little review on power as we learn about EMF and terminal voltage and internal resistance of things. This is how to deal with internal resistance. How are we doing with this? Questions, Josh? Point 1 is the voltage drop by, remember, if the terminal voltage is 11.9 with a 12 volt EMF, that means this voltage drop is 0.1. Right? I drop 0.1, I have 11.9 left. You good?